Thank you. And let's move on to the next presenter. He is also available now. Allan Cantle, the CEO of Nalasway Inc., and also Technical Director of OpenCAPI Consortium. And he's going to be talking about decoupling compute from memory storage and I/O with OMI, the Open Memory Interface. Allan Cantle is CEO of Nalasway, consulting on heterogeneous high-performance computing solutions. He's a well-known person for high-performance computing, in US and Europe. He's also the OpenCAPI Consortium Technical Director and Board Advisor. Previously, Allan was the founder of Nalatech, which during his 25-year tenure became widely known as a pioneer in FPGA accelerated computing. Before founding Nalatech, Allan was an electronics systems engineer and BAE systems developing real-time heterogeneous high-performance computers. He holds a degree in electrical and electronics engineering from the University of Plymouth. With this, I'm welcoming Allan for the talk, and he said that it's going to be a record session. He's available for question and answers. Allan, you want to introduce yourself a little bit and then start our presentation?
Yeah, thanks, Ganesan. Can you hear me okay?
Yeah.
So I see you're going to play the recording I sent you.
Yeah, Professor.
I've got mine set up as well if you wanted to do that, but
yeah. No, I'm fine with that. Whatever. Professor Satish, Allan can do the presentation to Satish.
It might allow me to jump around if people have questions at the end.
Shall I stop this?
Yeah, please take it out.
Okay, all right, that's great.
Yeah.
If we have problems, we can hand back.
Yeah.
Allan, so, please, you can share, please.
Yeah. So hopefully everybody can see my screen.
Yes, looks good, Allan. Please go ahead.
Okay. Okay, excellent. All right. So yeah, thanks for the introduction, Ganesh. Yeah, so I'll let this presentation do the talking. I gave it at the International Computing, International Conference on Supercomputing in Europe just a few weeks ago. It's got a lot of interest. I posted on LinkedIn. It's got an awful lot of interest, and it's talking about decoupling compute from memory storage and I/O with the open memory interface. So I'll let the presentation play, and if you want to ask questions through the presentation, I'll try and answer them on the fly, and we can take any more at the end as well. Okay.
Allan, can you please make it full screen?
Yeah, I'll do that now. Let me know.
Hi everybody. Yeah, my name's Allan Cantle, and I'm going to talk about decoupling compute from memory storage in I/O with the open memory interface. And this is an open source hardware initiative. For clarity, when you hear me use the word processor, please take it as meaning CPU and/or accelerator. So as an overview, firstly, I'm going to talk about why decouple compute from memory storage and I/O. And then I'm going to take a look at a bit of a step back at a top-down view of systems perspective, where the industry is trending, and also introduce you to some OCP, the Open Compute Project HPC concepts. I actually lead the actual sub-project in high-performance computing. Then I'll give you a basic overview of the open memory interface, and finally I'll bring it all together, seeing how we can decouple compute using the OCP OAM-HPC module with OMI. So without further ado, first section, why decouple compute from memory, storage, and I/O? Really, we need to start rethinking computing architecture, because the data is at the heart of computing architecture today. Compute is rapidly becoming a commodity. For example, the i386 it would retail today with its number of transistors at around 1 cent. Power efficiency and cost are really today's primary drivers, and that's what we need to focus on. And we need to be able to distribute the compute efficiently. It's not the center of attention anymore. So compute therefore needs one simple interface for easy reuse everywhere. So let's redefine computing architecture. Let's take it back to first principles, and let's with a primary focus on power and latency. So in computing, latency is the time taken to move data. More clock cycles equals more latency equals more power. More distance equals more latency equals more power. Hence, power can be seen as a proxy for latency and vice versa. And a focus on power and latency will beget performance, for sure. And we're already seeing this in the heterogeneous processors that have been coming to market for several years now, where they effectively optimize these for specific algorithm types on silicon. But we really need to do this for HPC now, so we need to focus our energy more at the system architecture level. And the silicon level is really taking care of itself to a certain extent. Touching on cache memory, so cache memory is bipolar, it has a bipolar relationship with power, which is our focus now, right? So its implementation really needs rethinking. Cache is very good for power efficiency. It minimizes data movement on repetitively used data. Cache is very bad for power efficiency. Unnecessary cache thrashing for data that's touched once or not at all. Many cache layers of cache equals multiple copies burning more power. Conclusion, hardware caching must be efficiently managed at the application level. Now, I'm not going to talk any more about cache, but I would like to ask for you to park your cache religion chip in your brain to one side when thinking about the rest of this presentation. It's an important topic, and we know it can be managed, but it needs to be thought about separately. But I won't go any deeper because I don't have the time. So today, if you're designing a processor, you've got many interface choices from a latency and a power perspective, you know, from memory all the way up to your distant networks over Ethernet, and the longer latencies and you burning more power. So your processor designers, they have to decide and allocate beachfront of their processor to each of these interfaces. And the choices are increasing at the moment, making it even tougher decision. And you can live and die by your choices. You may have the best processor architecture in the world, but if you don't choose the right interfaces for a particular application, you find your processor is useless. So this is the way of the world today. So could we simplify this to a shared memory interface? Shared memory has been extremely popular in HPC and the very old days of parallel computing. So could we successfully decouple the processors from the memory and storage and I/O with a shared memory approach? So this is showing you an abstract view of that. So we've got our processor and it's connected to nothing but memory directly with the lowest of latency and the lowest of power. So there's an instant benefit there. And as we reach out to the devices that are further away, we gracefully increase the latency and power and through the shared memory infrastructure. So that would allow processor companies to really focus on their core expertise, and they'll be able to support all domain-specific use cases because they just see everything as one memory interface. And so and as systems designers, we'll be able to actually use these devices for each of our applications effectively. So hopefully that answers the why. So let's take a step back and look at top-down systems perspective, and I want to introduce you to the OCP-HPC concepts as well. So today we're seeing disaggregated racks to hyper-converged chiplets. So so your classic server is really being pulled in a couple of different directions. And why is that? Well, if we look at the baseline is our classic server, we have physical composability. You can rearrange the devices, remove or add more memory and storage, etc. But in a disaggregated world, it's fully software composable. So none of your resources get stranded as you run different applications. But when you go to the chiplet world, the chiplet world, we really have very expensive physical composability. And I would even argue it's ill-conceived at the moment in the directions I'm seeing the chiplet world go from a composability perspective. From a power baseline, we see that node interconnect is in the 5 to 10 picojoule per bits inside the server. At the rack level, everything's further apart, so we're north of 20 picojoules per bit. And obviously the wonder of the chiplet approach is we're less than a picojoule per bit, which is the attractiveness of chiplets. From a latency perspective, again, you're adding more latency going up and down the rack, and you've got optimal latency in the chiplet. And then from a volume perspective, we've got the volume of the server. You get much bigger volume in your rack scale, and we're sub-cubic each. So you can see, it wouldn't be remiss in thinking that the hardware people focused on chiplets don't talk to the software people focused on composability. And I think you'd be absolutely right. And so can we really bring these two together? Is that possible? So it's really being torn apart, as I said there. So can we bring them together? So in the Open Compute project, they have open OCP Accelerator modules, and they use EDSFF interconnect for a new modular approach to attaching memory storage and networking. So I'm going to show you a module here that's been inspired by these standards. And hopefully I'll show you that this can bring the benefits of disaggregation and chiplets together under one modular standard. And you can see here we've got, it would be both software and physically composable. It would be power optimized to around 1 to 2 picojoules per bit, so not too far away from the chiplet world, and much better than the servers. We would still have a good optimal latency, and the module size is considerably less than the server. So I'll expand a little bit more on that. So fully composable compute module, again, leveraging the OCP's OAM module, and it's nicknamed OAM-HPC. On the left, you can see you still have your big, powerful processor on top of this module, and it could even be made up of multiple chiplets as well. So we're not throwing chiplet approaches away. And it has a multitude of interconnect on the bottom for connecting lots of different devices. Taking a closer look at that interconnect, fundamentally, we're proposing 2 different standards at the moment. One, we have 16 of the EDSFF 4C and 4C plus connectors, and we'll have 8 of the near stack connectors. That would give us a total of 320 transceivers for interconnecting from these processors to other devices. And that looks like this module. This one is just an example population. You can mix and match the population. That is the beauty of this approach. But this one's showing 8 E3.S modules. It can be media or memory, and 2 OCP NIC-free network modules, 4 4C cables for cabling to other devices, and 8 near stack cables in this little picture. So really we have a modular, flexible and composable module, and it's protocol agnostic. The hardware, the electrical signals are all fixed, but the protocol is dictated by the processor that gets populated on the module. And obviously some processors talk the same language, some don't. So, but that's important. This is protocol agnostic. The memory and storage in the I/O is interchangeable depending on the application need. And really, a processor must use HBM or have serial attached memory. This does not support parallel DDR memory. But even so, today, this module format could support NVIDIA Ampere, Google TPU, IBM Power 10, Xilinx FPGAs, Intel FPGAs, and Graph-Core IPU, to name a few. So this is a proposed approach in the OCP-HPC work group. Now, on the memory side, actually, memory I/O is finally going serial. There have been many failed attempts over the years, but I think we can say it's moving in that direction now. You can see the OMI DDIMM, Open Memory Interface DDIMM, was introduced in 2019, and an E3 format with 2 OMI channels was proposed in 2020. Smart Modular introduced a Gen Z memory module in 2020, and Samsung just recently announced a CXL.mem memory module in E3 format this year. So I think we can finally say that memory is going serial, so our modular approach will clearly be supported by these. Now, just going a bit more specific, let's just pick one of the processors, the IBM Power 10 OCP-HPC module as an example. You can see all the connectors I just showed you on the module surrounding the Power 10. The Power 10 has transceiver attached to everything. So here we can see we're supporting 16 OMI channels with E3.S modules with dual OMI on them. We've got a couple of NVMe SSDs plugged into the other ones in the E3 format. We have a NIC.3.0 OCP network card plugged into one of the other modules. And we have a cabled I/O giving you cabling off to some PCI attached device elsewhere. And then we have all the additional cables carrying the SMP and OpenCAPI buses. So this would be the protocol specifics of a Power 10 module that you could then use in this module format. But with this modular approach, so this is that module can be used today with any processor and any protocols and anything, you know, the classic way. But this dense modularity really does bring us a power saving opportunity by leveraging a potentially flexible chiplet level interconnect. So here I'm showing you an X-ray view of the module with the Power 10 on it and the interconnect underneath. And we can measure the Manhattan worst case distances between the die and the chip and the die, the ASIC die on the modules. And we're less than 5 inches worst case. So that really gives us an opportunity to reduce the PHY power to 5 to 10 dB budget and 1 to 2 picojoules per bit. So it's very similar to the extremely short reach standard XSR of the OAF standards. Also, we also have an opportunity to actually get rid of the packaging on these devices and actually use a substrate, use a module substrates as a package, so we get rid of the middleman, so to speak. And that would again increase power integrity and signal integrity further. And this is this approach with is challenging because of big substrates, but it's not beyond possibility. So we have an opportunity to greatly reduce the power consumption here. Let's take a look at OMI. So the open memory interface, the graph on the right is a log scale graph, and in short, it shows you that OMI has a bandwidth of HBM at DDR latency, capacity, and cost. So a little bit of a closer, it was introduced in production in 2019. This is not a pipe dream, this is available today and is very robust. But DDR4 and 5 has much lower bandwidth per die area beachfront, not physically composable. HBM is inflexible and expensive and is capacity limited. CXL.mem, OpenCAPI.mem, CSIC, they all have higher latency and they're termed really far memory, not near memory. And similarly, Gen Z is data center level far memory. So OMI is definitely the best serial attached memory approach to take. This is a bit of an eye chart, but I just want to highlight in yellow the memory interface comparisons. It's the ideal processor shared memory interface. The latency is very much on par with DDR, and the bandwidth is almost 10x per area that of DDR. And well, more importantly, is very similar to HBM. So because it's similar to HBM, that gives us an opportunity for HBM memory with an OMI-enabled logic layer interface. And that would make HBM much more flexible and have capacity options which aren't there today. So OMI should be considered as a logic layer of HBM going forward. This is another eye chart, but I wanted to leave everything for you all to see a bit of detail on the Power 10, but I want to highlight 3 things here. The OMI PHY, you can see it there on the actual Power 10 die. This is all to scale. The latency adder of the PHY channel is actually 2 nanoseconds in each direction. And you can see that it will drive today a 30 dB channel, so it takes 5 picojoules per bit, but there's an opportunity to drop that with the extremely short reach approach. So that's what I wanted to show you there. But here I also want to summarize this and say, let's look at OMI bandwidth versus our single precision FLOPS, because really OMI is helping to address memory bound applications that have been ignored forever. And so here, if we had a maximum reticule size die, we could fit up to theoretically 80 OMI channels on. That would be 5.1 terabytes per second. We know that NVIDIA Ampere's maximum reticule size gives you a 30 single precision teraflops. So, you know, you've got a 6-to-1 there of flops to bandwidth. But as die size shrinks, let's say we shrink it by 7 times the die, the OMI bandwidth reduction is only 2.8, but the flops reduction is 15. So we actually end up with a perfectly balanced 2 teraflops with 2 terabytes per second. So I don't think I've seen anything at decent performance, at least since the 60s or 70s to that level. So this is really quite interesting that we really are putting more attention on the data here. And we have plenty of capacity behind OMI that you don't have on HBM. So pulling all this together, let's see if we can build a decoupling the compute really truly with the OAM-HPC and OMI. So here I'm going to look at 1, 2, and 3 port shared memory buffer chiplets that we could create. And I'm going to show it in this module format. So the green box represents the OAM-HPC module, and we've populated a maximum reticle size processor with its 80x OMI XSR channels. Let's firstly add an OCP NIC 3.0 card with an OMI 3-port buffer chiplet on board. So we've got one port going to the main big processor. We've got another port which may interface to maybe a little acceleration processor chiplet. So you've got a second port into that memory. And then we've got the third port that would give us our fabric expansion to OpenCAPI, CXL, GMZ, Ethernet, InfiniBand, etc. So that could be implemented in NIC 3.0. In an E3.S module, we can have a 1 or a 2 port buffer doing something similar, the same. You know, you've got the main port to the processor. The second port could be to an accelerator. Actually this time buried in the buffer if that made sense to do so, and a little tiny accelerator. So that's another approach. As I mentioned, the HBMs, we could have a couple of HBMs attached using 8 of the OMI channels to give the same performance as HBM today. And so that would be a composable option. From an interconnect perspective, we could use a near stack, and we could put a 2-port OMI buffer chiplet on there to convert to the fabric standard of choice. And here you'd have the shared memory, a small amount of shared memory inside the buffer. So you don't need the external memory for this, but it's still the same shared memory approach. Or we could take the EDSF cabled connectors, and actually with those, we can actually populate that 2-port buffer, the same 2-port buffer, inside the connector itself. So we actually have a protocol specific active fabric cable. So imagine that you could plug a CXL cable in to plug to a CXL device, or an OpenCAPI cable in to plug to an OpenCAPI device, etc. This would be truly flexible with this approach. And finally, you could also, if you needed an OMI attached memory, but it wasn't directly local to this module, you could go for a medium reach extender buffer with less than 500 picoseconds of round trip delay adder to actually reach further away OMI memory. So hopefully this gives you an understanding of one memory interface where we truly have decoupled the compute from memory storage in IO. So once we have this module though, how do we use it? So the OAM modules actually plug into the OCP Accelerator infrastructure. So you can see 3 chassis from Inspur, Hive, and ZT systems. These are real, and they're being upgraded today to OAM version 2. They support 8 modules. So we can similarly support 8 of the modules I just shown you in that same 3U chassis and plug into the OCP ecosystem. The only difference is there is no motherboard. These would just mate to a water-cooled cold plate and also bring the power in through that cold plate. So and this would then plug into that OAI chassis. So in summary, we want to redefine computing architecture with a focus on power and latency. And we want that to be a shared memory-centric architecture. We can leverage the open memory interface for this, and we can use this dense OCP modular platform approach to actually to turn it into a practical reality. So are you interested? If so, how to get involved? From silicon startups to open hardware enthusiasts alike, I would encourage you to look at these steps we're taking. Firstly, join the OpenCAPI consortium or the OCP-HPC subproject. Replace your DDR memory with standard OMI memory interfaces on your next processor design if you're designing your own processor. Add a couple of low power OMI PHYs with this new XSR interface on any spare beachfront you may have on your processors so we can start to enable this transition to a completely decoupled compute from memory storage and IO. Build OAM-HPC modules around your large processor devices. Help the community build specific 2- and 3-port OMI chiplet buffers to go out to different fabrics like CXL or OpenCAPI, etc., and help the community to build OMI buffer enabled E3.S and NIC 3.0 modules as well. So I think we're already well underway with a lot of the efforts here, and bringing a wider community together will be great. So thank you very much. Any questions? And there are some links to the OpenCAPI Consortium and the OCP-HPC subproject. Thank you very much.
Okay. Did everybody get that?
Thank you, Allan. It's a very wonderful presentation. Definitely, there are people who may be interested already. Professor Satish from IIT Roorkee may have a lot of interest, and probably he will connect with you. And any other questions, participants for Allan? He is specially available here for you to check with him, any opportunities to work on OpenCAPI consortium and team panelists.
My contact details are there as well, and also links to both the organizations I mentioned.
Yeah, sure, Allan. And Professor Pratik, you have any questions for Allan? Sure. Okay. Looks like people probably will send you an email or something. But with this, thank you, Allan, again, for your time. Really appreciate it. And this is a kind of a long hour, nearly more than 4 hours. The workshop, and still people are active on that. And really thank you for all the presenters who have been who have done a wonderful job on presenting the various technologies from concept to solution. And this is what really required for the industries too. And there are a lot of opportunities to work on this open core foundation as well as OpenCAPI consortium. And people can get onto the projects and get onto the work group, and multiple opportunities are there. Where serious, a very senior technologists available to collaborate on this platform too. And this kind of the workshop with a lot of technology talk definitely will help the students, developers, and industry people to get onto the the latest and greatest the technology, and get hands on to it. And we are going to have Power 10 very soon from IBM, and also there are other things like Luke from Libersoc presented about the 180 nanometer tape out. There was an interesting talk too, and Satish Sadashivam from IBM talked about the power architecture and innovation in it, and also various the collaboration we can do with that. And also we talked about the Power 10 the features, those things definitely everyone will get an opportunity also to get access to that kind of system shortly. And as you know, like IIT Roorkee already set up an open power lab, and probably they would move forward with the Power 10 kind of hardware. And I would invite certainly IIT Roorkee to collaborate with us continuously. And it has been the journey with IIT Roorkee has been very wonderful, because they worked with us nearly 6 years through this open core foundation and the IBM the IBM technology all together. We had a wonderful session, and Pratik Narang's talk about the computer vision on the Power 9 really basically gave the good research ideas for students from IIT Madras and other people too. I have invited some people from the IIT Madras to be part of this, and even I welcome the Sinica team also joined this the workshop. I welcome them and really appreciate their time on spending last 4 hours plus with us. And overall this is a kind of a technology feast. Certainly, you will, if there are any questions or answers, or if you want to collaborate, please reach us out. You can reach us out, through email or our Open Power Slack channel. I'm going to share it with you all, and then we have a YouTube channel also for academia. You can certainly wait for these videos to be uploaded there, and you can replay the video, and you can reach us out on any hardware kind of access to. We do have some hardwares which we can provide to you for your deep learning exercises, high performance computing exercises, open CAPI exercises, and the power the ISA exercises. There are a lot of demos and other tutorials already created by many researchers worldwide. Those
hey,
are all, yep.
There are a couple of questions just coming in as well. If you
sure.
Yeah, sure. Carry on. I don't want to break into. I just want to let you know.
Yeah. There are a lot of videos and a lot of the tutorials and the lab exercises available with us, and reach us out. Quickly you will get up to the speed on the technology what we have today. And Allan, please go ahead for the questions.
Yeah, the first question is: are there open /Libra VHDL blocks for OMI? On the Libra piece, I'm not too familiar with the Libra piece. Somebody else may be able to help me out on there, but so I'm not familiar with anything going on there in terms of specifically to OMI, but that may well be a good idea. Certainly from a sideband management perspective, I think there are some significant things we need to get done on the sideband management with a system like this. From a VHDL perspective, there are two platforms that Ganesan may be able to help you get your hands on. They're called Fire and Ice. So Fire is a Xilinx FPGA platform that has host RTL for a host controller on the OMI, and also some test vector engines. And in fact, the memory people started to use that platform initially to test out the memories that they've been manufacturing. That one has RTL in it, and then there's a buffer platform called ICE. No, sorry, hang on a minute. Apollo and Gemini are the platforms. So Apollo is the host platform, Gemini is the buffer platform, and there's RTL for the buffer design. The RTL has the name Fire for the host RTL and ICE for the buffer RTL, and they are fully open sourced and released on GitHub today. There is a website actually that's just been launched, and it's not in my presentation because it's literally just been launched, but it's openmemoryinterface.org, I believe. And you should be able to find some details there. Again, Ganesan should be able to help point you in the right direction for that side of things. And there was one other one. This seems like a good opportunity to avoid the closed NDA required DDR5 problem. Absolutely, and I'm not sure if earlier presentations covered that topic, but we are actively trying to help out. Yeah, an OMI channel into a DDR with an implementation with a DDR buffer, open source DDR controller, would be a fully open sourced a buffer that could plug straight in to anybody's system that supports OMI. Okay. That was it.
Yeah, thank you, Allan. Thank you. It's good, and I will for Liber, I will definitely get back to you guys. Richard Wilbur, I will get back to you on the Liber side, and overall, the sessions went very good. Satish, you want to add a few things on top of that and close it? Professor Satish, you muted, please. Yeah.
Almost you covered almost all the things, and I just wanted to convey my thanks to all the speakers on behalf of IIT Roorkee, first of all, and to you for providing this platform and providing all the speakers and facilities. And yeah, so yeah, as I already mentioned, Satish had presented wonderfully well about AI and the power process and their developments. And yeah, he also spoke about how IoT, mobile, 5G kind of new architectures will get benefited with power processors. And I'm happy to learn that Power 10 is releasing soon, and IIT Roorkee will be in the forefront to adopt always the open power technologies. And yeah, we are looking forward to have open power machine with Power 10 processors too. And yeah, thanks to Luke, his talk on 180 nanometer tape out experience using open power ISA is excellent. And yeah, and I'm very glad that he was very active and addressing all the questions live, and he's very responsive to the people. And thanks to Luke for your active responses. And okay, and thanks to Professor Pratik for delivering a nice talk on his research particularly. And as Ganesan already mentioned, the research ideas are very important, and we are more into academics, and most of the participants joined here are academicians, and they look forward for good like research oriented outcomes and projects. So I trust, I mean, I request all the participants to be in touch with Ganesan and all other speakers, panelists, to have the resources of open power technologies. You can even actually get all the resources online. So your laptop is sufficient enough to access resources. So we can give a lot of research projects to you, and we can give the resources online. What just you need to do is you can develop a lot of projects in collaboration with all of us, and you can publish good papers using open power technologies. As Pratik did, you can also do a lot of good research using open power technologies. And though we couldn't hear Chekuri, but as Ganesan said, he will provide you the resources from his end. And James and Allan did a wonderful presentation. Particularly, I'm excited about power process, and yeah, that kind of like penetration is required, because the devices are becoming smaller and smaller day by day, and no more mobiles, no more desktops. All those devices are becoming, I mean, the market share is getting reduced day by day, and we will see only the small devices. Maybe soon we will talk about only smart dust, where only every dust particle is a sensory device, can act like a screen, can act like a keyboard, can act like your processor and all. So we are talking about that era where power technologies also need to adapt to such developments, and such miniaturization of power technology is very, very interesting and important. And I'm really excited to know about Power Pi process. And yeah, so we wanted to have such the participants, on behalf of participants, I just wanted to convey to the panelists that we want similar research directions and dimensions in these areas, and please keep us updated, and we will be organizing similar courses and workshops in the coming time, and your contributions and time is very important for all of us, and we look forward to hear you soon about further recent developments in this domain. So thanks, Ganesan, for making this workshop possible and sparing a platform. Thanks a lot.
Oh, thank you, Satish, and thanks to everyone, who were stayed, for last 4+ hours, and really appreciate it. Thank you very much, and we look forward to work with you in future workshops and future project collaboration. And thank you to all the presenters too, who basically spent a lot of time on preparing the presentation and being with us, for some time and answering the questions too. Thank you all.
Thanks to all the participants for joining the session. On behalf of our organizers, on behalf of IIT Roorkee, I'd like to thank all the panelists, Ganesan particularly, and all the participants. And we announce the closing of the workshop now. Am I right?
Thank you.
Ganesan?
Yes, thank you.
Yes.
Thank you, Satish. That's right. Thank you for your time too, Satish. I really appreciate it. Thank you.
I think this is the first conference which held for a longer time.
Yes, Satish, in India. Yeah, thank you.
In India, yes.
Thank you.
Okay,
Thank you.
thank you so much.